The James Webb Telescope just rewrote everything we thought we knew about the universe's first monsters, and the first discovery is something almost nobody predicts. Stay tuned to the end for the most mind-blowing revelation. Imagine looking back 13 billion years to a time when the universe was still shrouded in darkness. James Webb's NIRCam captured faint patches of infrared light that correspond to the earliest galaxies, some of which host nascent supermassive black holes. These objects are so distant that their light has traveled for more than 12 billion years to reach us, offering a direct window into the epoch when the first massive structures ignited. The data reveal compact, star-forming regions where black holes could have formed from the collapse of massive primordial clouds. By measuring the spectral signatures, astronomers can estimate the black hole's masses and growth rates, hinting at a rapid assembly process that challenges earlier timelines. This glimpse not only pushes the frontier of observable history but also sets the stage for the surprising discoveries that follow.
Surprisingly, JWST spotted quasars that shine brighter than models predicted for such an early era. These luminous beacons, detected in the near-infrared spectrum, emit more energy than a trillion suns, dwarfing the output expected from black holes only a few 100 million years after the Big Bang. Their brilliance suggests that they are accreting matter at extreme rates, feeding on surrounding gas clouds with astonishing efficiency. The observations force scientists to reconsider the limits of black hole feeding mechanisms, as conventional theories struggle to explain such luminosity so soon after cosmic dawn. Moreover, the brightness makes these distant objects easier to study, providing rich spectral data that reveal the composition of their host galaxies. By comparing the observed intensity with theoretical limits, researchers are refining the physics of radiation pressure and accretion disk dynamics, opening a new chapter in our understanding of early cosmic power sources.
In 2026, researchers reported a black hole weighing an estimated 1.5 billion solar masses when the universe was just 700 million years old. This staggering mass is far beyond what conventional growth models would allow in such a brief cosmic window. The finding emerged from spectroscopic analysis of the quasar's emission lines, which indicate the velocity of gas orbiting the black hole and thus its gravitational grip. If the mass estimate holds, it implies that black holes can either start from unusually massive seeds or grow through exceptionally rapid accretion episodes, perhaps aided by dense, metal-poor environments. Some scientists propose that direct collapse black holes, massive gas clouds that bypass star formation, could seed these giants. Others suggest that frequent galaxy mergers in the early universe supplied the necessary fuel. Either way, this massive outlier reshapes the narrative of black hole evolution and fuels intense debate across the astrophysics community.
Researchers uncovered that many early black holes reside in surprisingly small, dust-rich galaxies that were previously invisible to optical telescopes. JWST's mid-infrared instruments pierced through thick clouds of cosmic dust, revealing compact host galaxies whose stellar masses are a fraction of those seen in later epochs. These hidden galaxies challenge the assumption that the first supermassive black holes required massive, mature hosts to thrive. Instead, the data suggest that dense, dusty environments may actually promote rapid black hole growth by funneling cold gas toward the central engine. By analyzing the spectral energy distribution, astronomers can estimate the dust temperature and infer star formation rates, which appear elevated despite the galaxy's modest sizes. This discovery highlights how the infrared capability of JWST opens a new window onto the concealed corners of the early universe, where the most powerful black holes may have been quietly assembling.
One clue came from the unusual abundance of heavy elements in the gas surrounding these early black holes. JWST spectrographs detected strong emission lines of carbon, oxygen, and nitrogen, indicating that the interstellar medium had already been enriched by previous generations of massive stars. This chemical maturity, observed when the universe was less than a billion years old, suggests that star formation and supernova explosions occurred swiftly enough to seed the environment with metals. The presence of these elements also influences cooling processes, potentially accelerating black hole accretion by allowing gas to collapse more efficiently. Moreover, the metallicity measurements provide a timeline for the buildup of the first stellar populations, linking black hole growth with early galaxy evolution. Such chemical fingerprints are vital for reconstructing the sequence of events that led to the rapid emergence of these cosmic giants.
Hidden in the data was evidence that these black holes grew at rates faster than previously thought. By modeling the luminosity and spectral shape of the quasars, scientists inferred accretion rates approaching or even exceeding the Eddington limit, where radiation pressure typically balances gravitational pull. Some objects appear to be in a super-Eddington phase, swallowing matter at a pace that would double their mass in just a few million years. This rapid growth could be sustained by dense, cold gas inflows triggered by early cosmic structures or by turbulent conditions in their host galaxies. The implication is that black hole seeds did not need to start extremely massive. Instead, they could start modestly and balloon quickly under favorable feeding conditions. These findings push theorists to refine simulations of early universe dynamics, incorporating mechanisms that allow sustained, high-efficiency accretion during the universe's first few 100 million years.
Few people know that galaxy mergers likely fed these giants during the cosmic dawn. JWST's high-resolution imaging captured distorted morphologies and tidal tails in several host galaxies, signatures of recent or ongoing collisions. When two proto-galaxies merge, their combined gas reservoirs can channel large amounts of material toward the central black hole, igniting intense accretion bursts. Simulations support this scenario, showing that frequent mergers in the dense early universe provide a natural pathway for rapid mass buildup. Moreover, the merger process can stir up the surrounding medium, creating shocks that further compress gas and enhance cooling. By correlating observed merger features with black hole mass estimates, astronomers are building a picture where hierarchical assembly and black hole growth are tightly intertwined from the very beginning of galaxy formation.
Deep within the infrared spectra, JWST detected echoes of ancient accretion events that reverberated through surrounding dust clouds. These infrared echoes appear as delayed, broadened emission features, indicating that powerful outbursts from the black hole illuminated nearby material long after the initial flare. By measuring the time delay and spatial extent of the echoes, researchers can estimate the size of the dusty environment and the energy released during past episodes. This technique offers a novel way to probe the variability of early quasars, which are otherwise difficult to monitor due to their vast distances. The echoes also reveal the geometry of the surrounding torus, shedding light on how early black holes interacted with and shaped their host galaxies. Such insights deepen our understanding of feedback mechanisms that regulate star formation and black hole growth in the young universe.
Meanwhile, theorists revised models to accommodate the JWST findings, proposing new mechanisms for early black hole formation. One emerging idea suggests that massive primordial gas clouds could collapse directly into black holes without fragmenting into stars, creating seeds of hundreds of thousands of solar masses. Another hypothesis involves exotic physics, such as the influence of dark matter spikes that accelerate accretion. Computational simulations now incorporate stronger radiation pressure feedback and more realistic chemical cooling pathways, aligning better with the observed metallicities and growth rates. These updated frameworks aim to reconcile the unexpectedly large masses and high luminosities seen at redshifts beyond 8. As the community iterates on these models, the dialogue between observation and theory becomes increasingly dynamic, promising a richer, more nuanced narrative of how the universe's first colossal black holes came to be.
Finally, JWST's discoveries point toward upcoming missions that will probe black hole origins even deeper. Projects like the proposed Lynx X-ray Observatory and the European Athena mission aim to capture high-energy signatures from the earliest accretion episodes, complementing JWST's infrared view. Additionally, next-generation ground-based facilities such as the extremely large telescope will deliver unprecedented resolution, allowing astronomers to resolve the host galaxies of the faintest quasars. These instruments will test the direct collapse scenario, measure the spin of ancient black holes, and map the surrounding intergalactic medium with exquisite detail. The synergy between JWST's legacy data and future observatories promises to unravel the remaining mysteries of how the first supermassive black holes ignited, grew, and shaped the cosmos we observe today.
We've traveled from the faint glow of the cosmic dark ages to the bold new models that scientists are building around James Webb's revelations. The story of these early supermassive black holes shows how a single instrument can upend decades of theory and spark fresh curiosity about our cosmic origins. If you enjoyed this journey, hit the like button and subscribe so you don't miss the next mind-blowing list we'll explore each week. Which finding surprised you the most? Let me know in the comments below. Your thoughts keep the conversation alive.